Good morning, students. Today we will discuss the Pointing theorem and power flow in an electromagnetic wave. So for that purpose, let us consider a transmitter and a receiver, and we know that the transmitter converts any voltage and current waves into electromagnetic waves. So if any wave is propagating from transmitter to receiver, then in today's discussion we will try to find what will be power in this electromagnetic waves. For example, let us consider this surface, and what will be power in the wave that is crossing to the surface. Until now we have studied the electric and magnetic component of electromagnetic wave. We know attenuation, phase, etc. We can find these parameters very easily for any wave. So in today's discussion we will try to find the power that is available in the wave when it is crossing to any surface. So for that, let us write some equations that are governing this electromagnetic wave nature. So the first equation is, we have the curl of H is equal to sigma E plus epsilon del E over del T. We have this equation and we have discussed this already in detail. And the next equation that we know regarding electric field component that relates between E and H is equal to del H over del T related to induction. This is the second equation. We know these two equations. Now let us apply some mathematics to find the power equation from these two equations. So for that purpose, let us do some mathematical modifications. Let us do E dot first equation. Similarly, E dot sigma E epsilon del E over del T will be there. Now this can be written as sigma E dot E, taking sigma outside, we can write like this, plus epsilon E dot E divided by T, we can write, and E dot E is nothing but E square. Okay, so that is absolute value, plus epsilon, it can be written as, if we will bring it inside, then it can be half E square by del T, we can write like that. Okay, so the first equation, when we will do dot product with E, we can get this equation. Okay, similarly, let us do dot product of this with H. So when we will do dot product of del cross E with H, then we will have minus H dot del H by del T. After further simplification, we can have similar to this del H square divided by del T. Now let us do E cross H. We are doing this to find the power equation. When we will bring all together, then it will clearly tell us why it is important. So this equality we can write. For that purpose, let us take the help of the well-known equality, that is, if we have del dot A cross B, then in this case we have well-known relationship, that is B dot del cross A minus A dot del cross B. Following this, simply follow this to find the equality here. On the basis of that, it will be H dot del cross E minus A will be there, that is E dot del cross H will be there. And if we have this relationship, we have this and this already known value. Not only this, we have this term and this term from here. So put it in equation third from this is equation third, fourth and fifth. Put these values from equation 3 and 4 in equation 5, and we will get del dot E cross H will be equal to the, at the place of this we can write minus mu, okay, bring half here, minus half mu del H square over del T, and with minus sign E dot del cross H can be written as minus sigma E square, minus is for all, so it will be minus half epsilon del E square over del T. We have this relationship. Name it equation 6 and rearrange to make it simpler. E square minus we can take del over del T outside from both of these. Inside will be half mu H square plus half, minus has been taken out, so inside it will be plus epsilon E square. Now this is the final equation in front of us, that is E cross H. Okay, now let us try to find what these are. So let us come at this point, that is sigma E square. What is this? Let us try to find. We know current density J can be written as sigma E, and the unit of this is ampere per meter square. That is the current density. If we multiply from E, then we will get this equation, this term, and if we put the value of unit of E, that is volt per meter, then the top term is nothing but VI, and the VI we can say it is power. Okay, that is power per meter cube. What it means? This is the power density of this wave which is governed by these equations. Okay, so we can say this is the power density of the wave. Now come to this point. This is energy density in magnetic field. Now magnetic energy density divided by T. So energy density divided by T. Okay, let us write it here. del over del t half mu h square. This is energy density. Energy density. And if we have energy density and we divide by T, then it will be power density. So again we can write it watt per meter cube. Similarly, electrical energy density. This is electrical energy density divided by time. It will be electrical power density, that is watt per meter cube. In this way we find this is the power density and power density. Okay, so what we find from here? We find that at the right side we have the power density terms, and if we integrate over a given volume, then we will get power. That is on the basis of general understanding we can say this. So if we integrate over a given volume, that will give us a power. So let us do that. For that purpose we will do del dot E cross H integrate this over given volume dV is equal to minus sigma E square given volume dV minus del over del T half mu H square plus half epsilon E square over given volume. Again it will give us like this. So in this way, this is the power and it should be power. In this way we can say this is the power in the wave which has conductivity sigma, permittivity mu, and permeability mu and permittivity epsilon of the medium. So if wave is propagating in a medium which has this value, then that has power that is written here. Okay. Now let us talk about this term only, this full term. The medium has some conductivity. Okay, so then this is the power dissipated in form of heat due to the conductivity of the medium by electromagnetic wave, and this can be written as for full rate of decrease of energy, rate of decrease of energy in the form of E and magnetic field. So we can name like this, as we find this and this both are rate of decrease. So from here we can say that the wave power as it propagates, it decreases in the medium. Now let us consider a wave is propagating in a medium which has conductivity different from 0, permittivity and permeability. So in this case, as wave propagates, its power decreases in electric and magnetic field. We have discussed this, and that power that is decreases from the wave will be thrown out from the system, from the medium, that is due to the negative sign. So power flow outside of the volume of the medium, we derived or we find out that was del, I think it was E cross H. Okay, this was the power flow outside of the volume of the medium. Now we find it is for given volume. Now let us transform into surface. That is possible by divergence theorem, in which we can say surface and volume can be related. For any closed surface, there is any vector A dot ds can be written as volume integral of del A. We have this, and if relate from here, if we replace A by E cross H, what will be there? It will be exactly same to this. So we can have E cross H dot ds by replacing A from this will be equal to the del dot E cross H dV. This equation will be here. So in surface integral form, it can be written as like this. So now relate the previous findings. At the place of this, we can write E cross H dot ds. It was equal to the sigma E square dV for entire volume minus del over del T half epsilon E square plus half mu H square del dV for entire volume. We can put volume here, volume. We already have derived these two terms. From here, this is the power loss, or we can say power leaving to the volume, and this is the rate of decrease of electromagnetic energy, or we can say power loss of electromagnetic wave. So in this way, this total is the decrease in electromagnetic energy per unit time. So that is, we can say, power loss from given volume. So these, including these two, we can say this is total decrease in electromagnetic energy per unit time, and due to per unit time, we can say this is power loss from volume, from the entire volume. Now let us write E cross H as a third vector that is named as P. Now put the P at the place of E cross H. We have P dot ds. What is this? Related from the Gauss law. This is the outward flux of vector P leaving the surface, or we can say it is related to volume, so leaving the volume. So it is the outward flux of vector P that is leaving the volume. We can say that P is the power density per unit area. Power density per unit area. Here this is the power density per unit volume, and if we have P dot ds, then we can say same as power density per unit area. Now we know that E can be written as propagation in the z direction, E naught e to the power minus alpha z cos omega t minus beta z. The component of E is in the direction of x. The unit of this is volt per meter. At the same time, H can be written as, that is E naught divided by mu. It is remains same with some lagging angle, that is theta, name it either mu or n. It will be normal to that in another direction. If it is propagating in z direction, this is in x direction, then it should be in y direction, and the unit will be ampere per meter. Okay, so we can write P as like this: E cross H. Instantaneous of value of E can be written like this, instantaneous value of H can be written like this. Then we can write instantaneous power like this. Okay, so this is the instantaneous power density per unit area, and this is the instantaneous, or we can say it is named in another way, instantaneous point vector. This is a vector, so it is also named as instantaneous power vector, pointing vector, pointing vector. Actually, the scientist named this at his name, that is instantaneous pointing vector. Okay, so if we have closed surface like that, then it is the instantaneous power through closed surface. Okay, and if it is written like that, P dot ds, then it is the instantaneous power. Instantaneous z t, that is understood, I am not writing this is. Then we can say this is the instantaneous power through open surface, that is not the closed. So open surface means closed surface and open surface. Let us try to understand. For example, there is in a cube and wave is propagating from here and it comes out like that. In this case, at any surface, if we try to find the power in the wave which is crossing this surface at any instant, we wish to find the power, then that is this. And if we wish to find the power, instantaneous power for closed surface, then it means we will find the power at this surface, next surface, next surface, next surface, next surface, and so on from here to here. So we will find the power at the surface and add up to next one, to next one, next one, next one. So that will be the closed surface power.